Thank you, Henning, for introducing me. And I would also like to welcome all attendees of today's webinar titled From Idea to Optical Microassemblies, How We Assist in Design and Prototyping. For a start and for an overview, I would like to first give you a short introduction of Fraunhofer IZM, and then next show you what ways we propose in our group optical interconnection technology to integrate photonics and electronics on panel level or substrate level, as Henning called it, and in a highly scalable manner. I'll show you then thin glass design approaches to reach efficient optical coupling and concepts that we have developed in recent years. And of course, I will show you key technologies and equipment we use in realizing such systems. So for a start, Fraunhofer IZM, just to give you a quick intro, offers a world-class high-tech environment. We have facilities right in the center of Berlin and additional sites in Dresden with a wafer foundry and Cottbus, where we have a RF design team. We have about 5,400 square meters of laboratory space and 69 labs and measurement rooms. IZM operates different lines for electronic and photonic system integration and packaging solutions. These are wafer and panel based. So to give you a quick overview, the interconnection approaches in wafer and panel fabrication technologies, they become increasingly similar, and both actually use thin glass. Just to point out some facts, we have a certain lines and space resolution on panels, which is not as fine yet as on wafers, and we typically use organic substrates in panel level technology as compared to silicon, mostly in the wafer line. And the point, however, is that panel level technology is permanently getting better in the line space resolution, and it can almost match wafer level packaging structures for many applications. So Fraunhofer IZM is bringing R&D into application, and IZM is creating various types of system integration for use in medical engineering, industrial electronics, information and communication technology, mobility, and semiconductors. And with this overview, I would like to move on to the group that Henning was mentioning, that is looking at photonics and how to integrate photonic into assemblies. So we are a photonics group within an electronics institute, but we are getting more and more important with photonics being used in many more applications. And we have 3 teams that focus on different aspects of optical interconnection. These aspects have also been covered in previous webinars and presentations, and we can send you links to check that as well. Today, I would like to show you what aspects reappear and can actually be combined in a generic thin glass packaging approach. So we believe that thin glass is enabling integration and interconnection of photonics and electronics. And this is a highly adaptable and scalable hybrid integration approach, as I would like to show you here. You can embed thin glass in PCBs. You can use the edges and the inside of this thin glass. We can integrate photonic waveguides into the glass and do all types of routing for optical interconnection. We can place on either larger panels or smaller panels also circuitry or laser diodes and photodiodes. And we can also then go ahead and use the surface of this thin glass, and we can put optics on this glass, and we can align optics, and we can also introduce optical fiber feeds. We can create free space beams on a solid bench and include many micro-optical elements of different functionalities. To give you an overview or an example, I would like to show you a rather large glass-based assembly. This is a system for reading out and processing signals from an external optical fiber sensor. To go into the details of this glass box on a footprint of 50 by 100 millimeters, there's a fiber that feeds into the system, and there are 4 fibers going out of this box. And in between, there's an open space beam and electro-optical components that can shift wavelengths, that can split light, that can couple to and from optical fibers. We have electrical circuitry included. We have some preamplifier circuits and some transimpedance circuits to read out via electrical cables signals. And this system integrates frequency-based beams, modulators, and splitter chips, as I said, micro-optics, and how it is put together. We do this with a sequential active alignment, and we have certain ways that we can fabricate such systems in an automated manner. We also have metallization included that can be soldered to, that can be wire bonded to, and we have electro-optical and electronic features. And this box, as such, is then included in a rack, industrial rack, for the actual system that is being used. To show you a smaller assembly, these medium-sized ones pictured here, they include extensive electrical and thermal interconnects in different metallization systems. So depending on the application, we have different thicknesses of the metal and can create all parts that are needed for electrical circuitry and connection, as well as heat conducting paths. If you scale to smaller assemblies, then new ideas arise. We have proposed a thin glass assembly concept that can scale even smaller, and that is planned to replace gold box packages, which are expensive and not very flexible in creating systems. So we replace gold boxes of traditional systems, and we create small stacked glass packages which can efficiently be produced. These glass packages actually can also contain optical windows and optical facets, and we utilize laser structuring equipment to fabricate such stacked packages. And of course, the other components like lasers and lenses still have to be put inside these packages, but parts of the package really are used optically, and you can place this type of optical chip scale package, for example, directly on a PCB. We can also put metallizations on glass, and of course these can also be scaled down. And we can create very small redistribution layers on interposers, for example. This has already been shown in a previous webinar. And for very small features, at some point we have to go again to wafer level production schemes and wafer capping approaches to get hermetic packages that can be placed in systems. We recently had packages fabricated also in the Photonic Leap European project. So we see a lot of opportunities for thin glass panel packaging. Ever more complex photonic systems are needed. And there are waves of optical interconnection and integration. And the latest one is quantum tech packaging. And what appears there is that we have typical components that have to be placed on a glassboard as we propose it, and realizing different functionalities for a quantum tech system. So to go into more detail and what can be utilized with the technology that we offer, here a side view of an integrated atomic vapor cell. And so we can create a hermetic package locally or generally, and we can have the coupling, evanescent coupling to optical fibers, for example. So how do we realize glass-based scalable photonic assemblies on panel level? So we have a full line of industrial machines. They are used in a sequence to create, for example, the structured metallization. And this is used for electrical circuits, but also for creating the integrated optical waveguides. And laser structuring and coding machines are getting used, and we have fine-tuned processing to have ever smaller features. To show you one of our workhorses, and this is a combined laser machine which is doing glass structuring and optical facet creation. So a CO2 laser is being used for scribing, for creating cuts and facets with optical quality. And we furthermore can use this machine for the singulation of smaller packages and smaller chips from large glass panels. And we can also use the built-in green laser at 532 nanometers, which is doing laser ablation, and that can freely shape panel glass and can manufacture holders, adapters, and plates that we need for the putting together of optical assemblies. This laser is also used for trimming of metallizations and can then do some fine-tuning after all other metallization processes have been done. So the other metallization processes basically look like this. You have laser structuring, you have metallization by vapor deposition, we have the patterning, the galvanization, and surface finish. After that, we can create additional individual package features, and this is like putting in cavities to put other components in, or to create the optical facets. After the structuring, after putting in components, we can stack, we can seal the package, and be singulated from large glass panels. So this is the glass stack optical chip scale packages that we are proposing. We can also proudly present today our latest femtosecond laser machine. And this is allowing us to integrate even more processes. This has a 1030 nanometer wavelength for structuring glass in 3 different processes. We have selective laser-induced etching, where we use wet etching with KOH or specially developed smoothing agents. And we can also have glass welding and fusing. Or we can even include 3D waveguide writing without masks. On this machine, we can also switch from glass to polymer structuring. This has a 2-photon polymerization built in, so we can go to really, really small features and create optical lens elements and holding elements, as have been demonstrated before. You might also ask how we put our photonic systems together. And this is a slide on how we assemble optical systems. We do active alignment on industrial machines. We have a dedicated clean room with 4 machines for sequential alignment. And this active alignment means that we operate all light sources in the packages at full power, so we can really get the best alignment. And we have high resolution cameras for the beam profiling that is needed. And then the coupling results are fed back into the motion systems, so we get the best beams and the best chip and fiber coupling that's possible. Our results on industrial alignment machines are that we can adjust with 6 degrees of freedom. We have 200 nanometer resolution in XYZ and about 2 arc seconds around 3 rotational axes. And these machines are used for actual 24/7 production. So we can demonstrate that. And what we use is the shrink, minimized, or controlled gluing of components. For even higher accuracies, with up to 5 nanometer resolution, we have several alignment machines, and we use those for optical coupling analysis or quickly adaptable prototype. To show you also a recent trend, I said we normally glue optical components, but laser fusing is emerging, and we also have a dedicated machine that was developed also with a project partner. So we can directly fuse glass parts, optical fibers to chips, to micro-lens arrays with a high accuracy and with a high repeatability and automatization. So from idea to optical microassembly, starting to wrap up, how can we assist you in design and prototyping? We believe, and I have tried to show you today, that we have ways to integrate photonics in thin glass packages. So this is trying to reach stable and efficient optical coupling. And you really need the right choice of materials, of components, and optical designs. So I put in here a 2016 concept pictures, and we really have come a long way since. This was a rough sketch, and we really have managed to optimize this in many parts. So we could help you in finding and optimizing designs. There are many questions when creating a systems. Maybe you have answered them already, or we can help you in answering them. And this list is not complete. Yeah, there are so many aspects that have to be taken care of when putting together optical systems. We utilize our experience and our design tools for both vertical and horizontal optical coupling setups. And we always see in reality that we have to compare simulations and actual measurements. So we have several labs to align components and to also inspect what beams we have and can cross-check with what simulations we are doing. So from idea to optical microassemblies, why we believe in thin glass-based packaging solution. Glass is a cost-efficient base material that can be laser processed. The designs can be easily adapted in very short fabrication cycles, and we have a large panel level production machinery to use. There's a large scalability in size, complexity, and volume of the systems that we can fabricate. What components and functionality can be integrated? I showed you some examples. We can have an increasing number of light sources and optical facets. We can have wavelength and polarization control. We have an efficient coupling also to photonic integrated circuits and can couple to the outside world via optical fibers. We can include additional electrical circuitry and thermal connectivity to complete the system. How we do it? I showed you some of our design tools, our equipment, and the processing we can do on such packages. We are proposing a panelized fabrication, and this would be full systems, this would be simple interposers, and this can be even simpler optical chip scale packages. We are pushing the limits on industrial machines, and sometimes we also have to develop our own machines. And in all this, we're trying to answer new trends and find cost-conscious packaging solutions. Yes, time for me to wrap up and also point out that we will have a next date where a colleague of mine will show some advantages of wafer level fabrication and using passive alignment versus the active alignment I showed you today. With this, I would like to thank you for your attention. And yes, I hope you have some questions for me.
Yes, thank you very much.